Imagine being laughed at by your own superiors, dismissed as a dreamer, a fool, perhaps even a bit mad, for believing in something that no one else could see. In 1928, a 21-year-old Royal Air Force cadet named Frank Whittle stood before his peers with a proposal that sounded more like the plot of a science fiction novel than an engineering paper, a propellerless engine that could make an aircraft outrun the very wind itself. The establishment scoffed. Industry men rolled their eyes. And yet, behind those calm blue eyes of his, something was already burning. A quiet certainty that he had glimpsed the future. He was, without realizing it, decades ahead of everyone else. This is the story of how one man's relentless obsession forged the jet engine, the beating heart of modern aviation. Stay until the end, because the most astonishing turn in this story doesn't come when he invents it, but when he's nearly crushed by the very system his creation would later empower. Frank Whittle was born on June 1st, 1907, in Coventry, England, a city of clattering factories and sooty skylines, where the smell of oil and hot metal floated through narrow streets. His father, Moses Whittle, ran a small mechanical workshop that rattled with the sound of gears and tools, the rhythmic pulse of industry. For young Frank, that place was a cathedral. The hiss of steam, the spark of steel, the low hum of turning shafts. It was there that he learned to think with his hands. While other children chased footballs in the street, Frank disassembled old motors and puzzled over how they breathed, how they lived. He was only 7 when World War I roared across Europe. Sometimes he would stop whatever he was doing and look up at the sky as the rumble of aircraft rolled across the clouds. Those early planes, shaking, fragile, clumsy, seemed to him like mechanical birds wrestling against the wind. To most, they were noisy novelties of war. To Frank, they were promises. Flying machines, he thought, could one day free mankind from the boundaries of the earth. At school, he wasn't remarkable in literature or history, but in mathematics and science, he moved effortlessly. Teachers wrote that he could picture mechanical systems in his head, turning, shifting, operating, as if he were already inside them. He saw not just parts, but principles. By the age of 15, he had decided he would become a pilot. Nothing else made sense. In 1923, at 16, he applied to join the Royal Air Force as an aviation apprentice. They rejected him. He was too short, too frail, not built for the physical demands of flight. He tried again, rejected once more. Most boys would have stopped there, swallowed their disappointment, and chosen another path. Frank didn't. He began to train his body like he was training his mind, running before dawn, lifting anything heavy enough to strain, eating little, sleeping less. He was determined to outgrow his rejection, literally. 6 months later, in January 1923, on his 3rd attempt, he passed. The RAF finally accepted him into Cranwell, its most prestigious aviation school. There, among the rows of aircraft, the scent of fuel and canvas filled his lungs. The whir of propellers echoed across the airfield. He learned not just how to fix planes, but how to understand them. He absorbed flight theory, aerodynamics, and the fragile balance between lift and drag. His instructors soon noticed something unusual. Frank didn't just follow manuals, he challenged them. He wanted to know why. By 1926, his sharp mind and relentless curiosity earned him a rare promotion. He would train as an officer cadet, meaning not only a mechanic, but a pilot. It was the opportunity of a lifetime, and Frank made full use of it. During flight lessons, while others thrilled at the freedom of the open sky, he studied every vibration, every hesitation of the engine. He noticed how propellers strained when planes approached higher speeds, the blades biting the air until the tips screamed near the speed of sound, shaking as if the machine itself was rebelling against its limits. That idea haunted him. What if, he thought, You could fly without the propeller at all. Late at night, the dormitory quiet, except for the ticking of a distant clock, he filled notebook after notebook, sketches, calculations, fragments of ideas. His fellow cadets teased him, called him the dreaming mechanic. But Whittle was no dreamer. He was a man possessed by a question that refused to leave him alone. In 1928, just 21 years old, still wearing the crisp blue of a cadet, Whittle completed a thesis with an unassuming title, Future Developments in Aircraft Design. The title was plain, but the contents revolutionary. Within those typed pages, he proposed the foundation of the jet turbine engine. The idea was breathtakingly simple in principle, impossibly complex in execution. Instead of using pistons to turn a propeller, Whittle described a turbine driven by the thrust of hot gases that could push an aircraft forward directly. Air would be drawn in, compressed, mixed with fuel, ignited, and then expelled through the back of the engine. The result, forward thrust. Newton's third law, applied not to rockets, but to the sky. He knew rockets already worked on this principle, but they burned fuel too quickly, uncontrollably. Whittle's brilliance was in his solution: make it continuous, a closed system of compression, combustion, and rotation that could sustain itself. He designed three main sections: a compressor, a combustion chamber, and a turbine, each feeding the next in a perfect cycle of motion and energy. And at high altitudes, his concept would shine. Propeller planes gasped for air up there, their engines choking as oxygen thinned. But Whittle's engine would thrive, drinking the thin air and turning it into speed. The higher you went, the faster you could fly. When Whittle presented his thesis at Cranwell in October 1928, some instructors nodded politely, intrigued but uncertain. Others frowned, skeptical. Interesting theory, one said, but impossible in practice. The physics were sound, but the world of metal and machining was not yet ready. In 1928, even the best metals softened under the heat Whittle described, temperatures soaring past 1,000 degrees C inside a combustion chamber. Turbines would have to spin at unheard-of speeds, each revolution a battle against the limits of endurance. Precision manufacturing at that scale simply didn't exist. Compressors were clumsy, inefficient. Everything, it seemed, was stacked against him. Still, Whittle persisted. The RAF forwarded his thesis to the Air Ministry. For weeks, he waited, half hopeful, half resigned. When the reply came in January 1929, it was courteous, even complimentary. The idea, they said, was theoretically sound, but impractical with current technology. Too far ahead, too costly, too unnecessary. And just like that, his vision was shelved. Europe was resting in the uneasy calm between wars. The world wanted to forget conflict, not prepare for the next one. Military budgets shrank. Experimental dreams were quietly archived. A device that could make aircraft travel faster than sound seemed like fantasy to men who still believed biplanes were the future. Frank Whittle felt the rejection like a cold wind, but he wasn't angry, just disappointed. He knew they couldn't see what he saw. He once told a friend, "They think I'm chasing clouds, but clouds are where we're going." So he carried on. He graduated from Cranwell, commissioned as a pilot officer, and over the next few years, he became known for his precision, his daring, and his ability to fix almost anything that flew. He served as instructor, test pilot, engineer, all the while nurturing the same impossible idea. Even while standing on the tarmac, the smell of kerosene and the metallic hum of engines in the air, he couldn't stop thinking, we're still crawling through the sky when we could be soaring. In his off hours, he continued sketching designs in the margins of flight manuals. He thought about airflow, fuel compression, the shape of nozzles. To others, these were abstractions. To him, they were blueprints of destiny. He didn't yet know that his persistence would change the course of aviation, or that it would cost him dearly before it did. But in those quiet nights, under the pale hangar lights, you could almost see the spark of the jet age flickering to life, born not in a laboratory or a boardroom, but in the restless mind of one young pilot who refused to stop believing. And in that silence, with the distant echo of engines humming across the airfield, history seemed to take its first deep breath. In 1930, Frank Whittle did something few men of his age and rank would ever dare. He filed a patent for an invention that most experts dismissed as fantasy. He wasn't protecting a gadget or a curiosity, but an idea so radical it might change the sky itself. The young RAF officer understood that even if the world wasn't ready to build it, the concept of the jet engine needed to be safeguarded. With the quiet help of a few trusted colleagues, he drafted a meticulous application that laid out the principles of his design: compressors, turbines, combustion chambers, all bound by the logic of thermodynamics, and a dream of speed without propellers. On January 16, 1930, British patent number 347206 was officially granted. It was a victory, but one that came wrapped in a quiet kind of burden. A patent, after all, is not a trophy, but a promise that must be paid for each year. Britain's maintenance fees were modest by industrial standards, but for a young officer living on a limited salary, they were a drain that gnawed at his every paycheck. Yet Whittle paid them himself, year after year, hoping that one day someone would see what he saw: the clean, elegant logic of the jet. Every pound he spent was a silent vote of faith in a future that seemed always one step out of reach. In the years that followed, he went door to door across Britain's aviation industry, pitching the idea with the zeal of a man convinced he'd glimpsed the next age of flight. Armstrong Siddeley, one of the leading engine manufacturers, showed interest at first. In 1929, they had even flirted with the idea of collaborating. But when the practical difficulties became clear, they quietly stepped back. The materials, they said, could never withstand such heat. The rotational speeds were unthinkable. It was, to their minds, an engineer's daydream. Bristol and Rolls-Royce didn't even reply. The industry, comfortable in its dominance of piston engines, had little appetite for a leap into the unknown. Their faith was in crankshafts and cylinders, not turbines and airflows. Within the RAF, Whittle's reputation began to bend under the weight of skepticism. Senior officers dismissed him as a romantic tinkerer, chasing visions better left to science fiction. "Mad Whittle," they whispered, half in jest, half in doubt. Some of his colleagues admired his intellect, but most quietly advised him to focus on his flying and leave the theoretical stuff to dreamers. And yet, in 1932, a small window of opportunity opened. Whittle was selected to study mechanical engineering at the University of Cambridge, an honor that few RAF officers ever received. For him, it wasn't just education, it was escape and validation. At Peterhouse College, he immersed himself in the rigorous logic of machines, thermodynamics, and the mathematics of airflow. The laboratories smelled faintly of oil and chalk dust, the sound of turbines and discussions echoing through old halls. He worked with a fierce, almost monastic devotion. Every problem he solved brought the jet closer to reality. His 1935 undergraduate thesis was no longer a dream scribbled on the back of flight logs. It was a comprehensive proof, full of numbers and equations, showing that a jet-powered engine could outperform any piston engine then flying. It was a quiet triumph of intellect over doubt. Still, even Cambridge had its skeptics. Professors warned that no known metal could endure the heat such a machine would generate. Others pointed to the poor efficiency of early turbines. Whittle argued back, politely but firmly, that new alloys, new techniques, and perseverance would bridge those gaps. But the more he argued, the thinner his wallet became. Maintaining his patent was bleeding him dry. By 1935, the inevitable happened. He could no longer afford the renewal fees. He let the patent lapse, a decision that must have weighed heavier than any academic exam he ever faced. With its expiration, his idea entered the public domain. Anyone, an individual, a company, even another nation, could now use it freely. At the time, it felt like a quiet personal failure. Years later, it would echo in ways no one could yet imagine. Yet even in that low moment, Whittle did not yield. He carried within him a quiet conviction that the jet engine wasn't just possible, it was destiny. If not me, he must have thought, then someone else. But deep down, he had already decided it would be him. When he finished his studies at Cambridge in 1935, fortune finally began to stir. Two former RAF colleagues, Rolf Dudley Williams and James Tinling, reached out to him. Unlike the doubters, they didn't laugh or pity him. They listened and believed. They weren't engineers, but they knew opportunity when they saw it. To them, Whittle wasn't a mad inventor, but a man a few years ahead of his time. Williams and Tinling recognized that what Whittle lacked wasn't theory, it was money. Building a prototype meant leaving equations behind and entering the workshop. Through their network, they introduced him to a financier named Lancelot Law White, a man fascinated by new technologies. White met Whittle in early 1936. Across several meetings, he saw not a wild dreamer, but a methodical mind, a pilot who could talk about combustion ratios with the precision of a scientist. White agreed to fund the project. It wasn't much, barely enough to start, but it was something. On January 27, 1936, they founded Powerjets Laurentide. Its purpose was simple yet audacious: to build, test, and someday sell the world's first operational jet engine. Whittle, now officially chief engineer, finally had a company, a team, and a fighting chance. But even with money, building the engine was no small task. Every component was uncharted territory. They needed a manufacturer with the precision and courage to attempt something entirely new. The British Thomson Houston Company, known for its work on steam turbines, agreed to help. It wasn't a perfect fit, but it was the best chance they had. In March 1936, real work began. The compressor was the first challenge, a small, big miracle of metalwork that needed to squeeze air to pressures never achieved in such a compact space. Whittle chose a dual-flow centrifugal design. Air would enter along the axis, then sweep outward in a radial motion. It was less efficient than a pure axial compressor, but it could be built with existing technology, a crucial compromise between theory and reality. The combustion chamber, too, was a monster of a problem. Airflow at those speeds was unstable, and keeping the flame steady was like holding a candle in a hurricane. Whittle's solution was ingenious: a ring of multiple chambers, each with its own injector and ignition system, encircling the engine's core. It looked complex on paper, and even more so in metal, but it might just work. The turbine, however, was the true heart of the challenge. It had to draw enough power from the exhaust gases to spin the compressor while still leaving enough energy to thrust the machine forward. It would spin at unimaginable speeds, its blades glowing with heat. Whittle designed a single-stage turbine, its blades forged from the best alloys Britain could produce. Throughout 1936 and 1937, progress was painstaking. Money was short. Every setback felt personal. The Powerjets team worked long hours for modest pay, surrounded by blueprints, half-assembled metal parts, and the constant rattle of tools. Whittle himself was often seen late at night in the workshop, scribbling equations in the margins of reports, running numbers again and again, as though trying to will perfection into existence. The strain began to tell. His health faltered, his sleep shortened, and yet he refused to slow down. At last, by April 1937, the pieces came together. The engine, strange, bulky, and beautiful in its own industrial way, stood ready in the test bay at BTH's Rugby facility. A forest of pipes, gauges, and wires surrounded it. It didn't look like a revolution. It looked like a jumble of metal barely held together by faith. Whittle stood before it, silent for a moment. 9 years of effort, mockery, and debt had led to this. He wasn't thinking about glory or money anymore. He just wanted to see it breathe. The first test was set for April 12, 1937. The small team gathered, engineers, technicians, and dreamers alike. The air was thick with nervous energy. Behind protective barriers, they checked every connection, every gauge. Whittle moved from one system to another, his fingers tracing the metal like a surgeon before an operation. Fuel was poured into the tanks. Electrical circuits hummed softly. An external starter motor was primed, ready to spin the compressor until combustion could take over on its own. At 7:45 p.m., Whittle gave the order. The motor began to turn. The shaft spun faster, 2,000 revolutions per minute. Igniters flashed. Fuel flowed. For a few tense seconds, there was nothing but mechanical whine. Then, a spark. A low, guttural rumble emerged. Then a roar. The chambers lit in. Sequence, and the turbine began to sing. Air and fire and motion fused into one living rhythm. The gauges leapt. 3,000 RPM, 4,000, 5,000. The jet engine was alive. Whittle stood there, eyes fixed on the machine, the roar echoing through the steel walls. After 9 long years, his impossible idea had drawn its first breath. Outside, beyond the test bay, the night was still. The last faint traces of daylight flickered on the horizon as a warm metallic hum lingered in the air, like the heartbeat of a new age waiting to begin. The noise was unlike anything anyone had ever heard. A piercing, metallic whistle, entwined with a deep, resonant growl that seemed to come from the bones of the earth itself. It wasn't just sound. It was pressure, vibration, raw energy compressed into music. That night in April 1937, the team stood frozen before it, feeling as if they were listening to the sound of tomorrow. But the future has a way of arriving violently. Something went wrong. The pitch climbed higher, faster. The gauges danced. 6,000 revolutions per minute, then 7, then 8. Whittle shouted to cut the fuel, his voice straining against the roar, but the engine had stopped obeying. It was running wild, feeding itself with its own fire. The vibrations grew unbearable. The entire rig trembled, metal on metal, the instruments clattering like nervous hearts. The sound turned from promise to threat. At 13,000 RPM, well beyond anything the design could safely endure, Whittle made the only decision a man could. He hit the emergency cutoff, cutting the fuel entirely. For a breathless moment, the engine refused to die. It wound down slowly, as if reluctant to surrender. Then, at last, the roar faded to a deep sigh and vanished. Silence filled the room, an almost sacred silence. For a few seconds, no one moved. Then someone laughed, half in disbelief. Others followed, their relief spilling into nervous chuckles. The tension broke, replaced by a strange euphoria. The engine had nearly torn itself apart, but it had worked. For the first time in human history, a jet engine had run under its own power. When they opened the casing after the test, the truth was plain. It was both a triumph and a warning. The fuel control system was clearly inadequate. It had allowed the engine to spiral out of control. Several turbine blades showed the scars of heat far beyond their limits. Bearings were worn, scorched by the violence of speed. Yet the fundamentals were proven beyond doubt. Air, fuel, fire, and motion. Each played its part perfectly. The machine had lived, breathed, and roared. Whittle was elated and utterly spent. The months of anxiety, the years of ridicule, and the sheer intensity of that night had drained him completely. In the days that followed, his body finally rebelled. The doctors called it a nervous breakdown. Whittle called it exhaustion. They ordered rest, But his mind wouldn't listen. Even in bed, he was sketching. Improvements in his head, fuel governors, cooling systems, turbine shapes. Sleep eluded him. The future kept whispering equations. News of the test spread quickly across Britain's aviation circles. The whispers that once mocked Mad Whittle began to change in tone. Some called him eccentric still, but now with a hint of respect. The RAF began asking questions, requesting reports, seeking details. For the first time, doors that had been locked for years began to open just a little. Maybe, just maybe, the young dreamer wasn't so foolish after all. Through 1937, Whittle and his small power jets team threw themselves into redesign and refinement. The concept was sound, but it was still raw, too fragile, too unpredictable for the air. Every bolt, valve, and chamber needed revisiting. Progress came in inches, but every inch was a victory. The first priority was the runaway fuel system that had nearly destroyed their work. The cause was a vicious feedback loop. More RPM meant more air meant more combustion, and more combustion meant more RPM, a self-feeding spiral of chaos. Whittle designed a clever mechanical governor, a sort of automatic brain for the engine. It would measure RPM and temperature, adjusting the fuel flow to keep everything in balance. Then came the combustion chambers. Whittle redesigned them entirely, aiming for a steadier, cleaner burn. He experimented tirelessly. Different injector nozzles, new air channels, modified chamber shapes. Some tests sputtered, others flared too hot. But gradually, through patient iteration, he found the balance between flame and flow. Each test told its own story in sound and vibration, and Whittle was learning to read them like a language. Materials remained a constant enemy. The heat inside the engine could melt or warp most metals. Together with metallurgists, Whittle began testing special nickel alloys and stainless steels, seeking that perfect combination of strength and resilience. Every new material was a gamble. Some cracked under strain, others corroded too fast. Progress came slowly, measured not just in data, but in burn marks and broken parts. Money, as always, was tight. Power jets lived in a state of near-permanent financial starvation. The company's survival depended on the faith of a handful of investors and the stubbornness of its founder. Whittle often covered costs from his own pocket, fuel, materials, even rent for the test space. He knew that every experiment risked not just failure, but ruin, yet he pressed on. By July 1937, the redesigned engine stood ready. This time, it behaved. The machine ran smoothly, its RPM rising and falling, under precise control. Combustion was stable, the roar clean and even. The gauges stayed calm. For the first time, the team could stand close enough to truly listen, to hear not chaos, but rhythm. There were still problems, of course, vibrations, heat spots, and inefficiencies. But the sense of progress was undeniable. They were no longer chasing theory. They were shaping reality. Through 1938, testing became routine, almost ritual. Each day brought new data. Each failure, another step forward. Whittle began to know his machine the way a pilot knows his aircraft, by instinct as much as by instrument. He could tell from the pitch of the exhaust whether combustion was rich or lean. He could feel, even through the floor, when the balance was right. Visitors began to arrive. Officers from the Air Ministry, men in dark coats and careful expressions. They watched, listened, and asked questions. When they left, some carried a quiet sense of awe. By late 1938, the ministry extended a modest development contract. It wasn't much money, but it was recognition. Whittle finally had official support, however small. Unbeknownst to him, the race had already widened. Across the Channel, in Germany, another engineer was pursuing the same dream. Hans von Ohain, working under the Heinkel Company, had started his own experiments in 1935, years after Whittle's first patent, but with far greater industrial resources. Neither man knew of the other's work. It was a strange symmetry of history. Two minds divided by borders and politics, converging on the same truth. In August 1939, the quiet rivalry became irrelevant. Germany invaded Poland. The world shifted overnight. Suddenly, what had been an engineer's obsession became a matter of national urgency. The British government, scrambling to keep pace with German rearmament, began to realize that Whittle's invention might hold strategic power. Funding increased. The RAF promoted him to squadron leader and released him from active flight duties. His mission now was singular: bring the jet engine from theory to the skies. More engineers were assigned. Workshops were expanded. The once lonely inventor now led a growing team. But with resources came pressure. Britain's survival was on the line, and technology had become its weapon. By 1940, as the Battle of Britain raged across the sky, every improvement mattered. British Spitfires and Hurricanes fought valiantly against the Luftwaffe's relentless assault, their piston engines pushed to the limit. In that desperate summer, speed and altitude became more than numbers. They meant life or death. And yet, across the sea, the Germans had already taken a small, secret step ahead. On August 27, 1939, just days before war broke out, a compact aircraft lifted from a runway near Rostock, the Heinkel H-178, powered by von Ohain's jet engine. It was the first true jet flight in history. The flight was brief, but it proved the concept. Only a handful of people knew of it. The event was classified, hidden even from much of the Luftwaffe. Von Ohain's design, the HS-3B, shared the same heartbeat as Whittle's. Both engines relied on the same thermodynamic principles, born not from imitation, but from parallel insight. The irony was cruel yet poetic. Whittle's expired 1935 patent had placed his concept in the public domain, meaning the idea itself was free for anyone to use. He had given the world the spark, even if another nation had struck the first visible flame. By early 1940, Whittle's own creation, now designated the W-1, was finally ready for flight. The Air Ministry contracted the Gloucester Aircraft Company to design a test aircraft around it. The result would be the Gloucester E-2839, a small, compact plane built not for war, but for proof. Every rivet, every panel, every joint was meant for one purpose: to show that a jet could truly fly. Construction went ahead at breakneck pace. Gloucester's engineers worked through nights and weekends, while Whittle's team continued bench testing the W-1. By December 1940, the engine had logged more than 100 hours of successful operation. The data was promising: steady thrust, reliable ignition, improved cooling. The machine that had once rattled itself nearly to pieces was now calm, measured, and alive with purpose. Outside, the war thundered on. Inside the hangar, another kind of storm was gathering: the quiet hum of metal and air, the birth of a power that would soon rewrite the sky. And on a cold morning, amid the faint scent of oil and the distant rumble of piston engines, a new sound began to rise: a low, steady whine that promised change. It was the same sound Whittle had heard years before. Only now, it no longer belonged to the future. The W-1 engine produced about 860 pounds of thrust, just enough to push the small Gloucester E-2839 to speeds that, while not revolutionary, hinted unmistakably at the future. It wasn't a combat-ready power plant, not yet, but it was proof, solid, humming, metallic proof, that Whittle's idea could truly fly. Behind the test stand and the endless reports, new dreams were already forming. More powerful models like the W-2, promising nearly double the thrust, 1,600 pounds of compressed energy waiting to be unleashed. By March 1941, after years of drawings, sleepless nights, and quiet despair, the E-2839 finally stood complete. Sleek, compact, purposeful, a shape that seemed to belong more to the decade ahead than the one at war. The W1 engine was carefully fitted, its tubing and rivets glinting in the dim hangar light. Then, under gray English skies, the machine was loaded onto a truck and sent north to RAF Cranwell. Ironically, this was the very place where a younger Frank Whittle had first scribbled down his impossible idea 13 years earlier. Time had turned that dream into metal. Ground tests began immediately. The engine roared to life, smooth and steady, its tone unlike any piston engine. It was a higher, purer sound, a turbine's keen breath cutting through the air. Everything worked. Yet the real test, the one that mattered, would happen in flight. In April, taxi runs began. Squadron leader Jerry Sayer, the test pilot, gradually pushed the throttle forward, feeling how the aircraft responded. The E-2839 rolled straight and true, its controls crisp. Short hops followed, just enough to lift the wheels a few feet off the runway. Each hop carried with it a little more confidence, a little more faith. May 15th, 1941, was chosen for the first full flight. The weather, as if in quiet cooperation, offered perfect skies and barely a breath of wind. On the airfield, a small group gathered, RAF officers, engineers, ministry observers, and at the center, Whittle himself, shoulders slightly stooped, but eyes alight with exhaustion and hope. 13 years of struggle, ridicule, and stubborn perseverance were about to meet the moment of truth. At precisely 7:40 in the evening, Sayer received clearance. The sunlight stretched long and golden across the grass as he eased the throttle forward. The jet began to roll, the whine rising, soft at first, then swelling to a clear metallic chorus. 60 miles per hour, 70. At 75, he pulled gently on the control stick. The nose lifted, and the wheels left the earth. For the first time, a British jet aircraft was airborne. The E-2839 climbed smoothly, effortlessly, as if drawn upward by invisible threads. Sayer kept low at first, just a few feet above the runway, testing how the controls responded. To his surprise, and everyone's relief, the plane handled beautifully. No vibration, no engine hiccups. Just a clean, steady rush of air over the canopy. On the ground, Whittle watched through binoculars, his heartbeat thudding louder than the turbine itself. He could barely speak. His dream, once dismissed as fantasy, now traced a silver line through the late afternoon sky. Tears blurred his vision. 13 long years, all the arguments, the debt, the exhaustion, the ridicule, were redeemed in this single, shimmering moment. Up above, Sayer completed a wide circuit of the airfield, climbing to about 1,000 feet, banking gently left and right. Every movement felt smooth and precise. The throttle responded instantly, no lag like the piston engines. It was like commanding a living current of air rather than machinery. After 17 minutes, Sayer lined up for landing. He brought the throttle back, gliding down steadily. The wheels touched grass with a soft bump. The E-2839 slowed, rolled, and came to rest. Sayer opened the canopy, smiling broadly. He had just written a new line in aviation history. Cheers broke out around the field. The engineers, tired, grimy, hollow-eyed, embraced each other with laughter and disbelief. Whittle stood still for a moment, overcome. He had carried this idea across years of doubt and near collapse, and now it had taken flight. His engine had not just worked, it had soared. Later, Sayer's official report described the flight as entirely satisfactory, praising the engine's smooth and reliable performance. The absence of vibration made the aircraft astonishingly comfortable to fly. The throttle response was quick and precise. On later tests, the E-2839 reached nearly 600 kilometers per hour, staggering for an early prototype. In the days that followed, the aircraft flew again and again, each time gathering vital data. Engineers measured everything: temperatures, stresses, fuel flow, vibrations. Each run revealed something new to refine, something to improve. The W1 engine accumulated dozens of hours in the air. Minor faults appeared and were swiftly corrected. But the foundation, the concept, was now proven beyond doubt. Word of the achievement spread quickly, climbing the chain of command until it reached the Prime Minister himself. Winston Churchill was briefed and reportedly expressed both fascination and urgency. The implications were enormous. If Britain could bring jet fighters to the front before Germany, the air war could tilt dramatically in her favor. By July 1941, the Air Ministry formally commissioned the development of an operational jet fighter. Gloucester was tasked with building it, the Meteor. Whittle's company, Power Jets, received official contracts to produce engines for it. At last, after years of being dismissed as impractical dreamers, Whittle and his small team had government backing and national priority. But the road ahead would be longer still. Building a single test aircraft was one thing. Designing a combat-ready machine was another. The Meteor would require twin engines for both power and safety. It would carry guns, armor, radios, all of which meant more weight, more heat, more complexity. Every system had to evolve together. And as Britain pushed forward unseen across the Channel, so did Germany. Though the British did not yet know it, the Luftwaffe was testing its own jet, the Messerschmitt Me 262. Fueled by vast resources and the industrial machinery of the Reich, German engineers advanced quickly. The race was not over. It had merely begun. Whittle, now promoted to wing commander, received honors, medals, and attention he had never sought. But celebration was brief. Pressure replaced doubt. Every hour mattered. The war was still raging above British cities, and each new test carried the quiet weight of lives, depending on the next improvement. Between 1941 and 1943, development reached a feverish pace. The W2 series engines evolved through countless refinements, each variant slightly more efficient, more reliable, more powerful. The W2B, introduced in 1942, produced nearly 1,600 pounds of thrust, twice the strength of the first engine. It was enough to lift real fighters into combat. But scaling production from a workshop experiment to mass manufacture was its own battlefield. Tolerances that could be managed by a handful of master machinists now had to be maintained by entire factories. A misplaced millimeter could ruin performance or cause catastrophic failure. Supply chains tangled. Materials ran short. Every turbine blade demanded rare alloys. Every combustion chamber required welding of near-surgical precision. The smallest details decided success or disaster. High-speed bearings had to endure revolutions no engine had survived before. The British industry, already stretched thin by wartime demands, struggled to meet these new standards. Yet, even as the technical challenges mounted, politics began to intrude. The government wanted tighter control, believing nationalization would speed progress. Established giants like Rolls-Royce and Rover circled, eager to secure their share of this new and vital technology. Tensions flared. Whittle, fiercely protective of his design, often clashed with officials and company executives. Rover, now responsible for producing the engines, made modifications Whittle viewed as careless. They, in turn, thought him too idealistic, too unwilling to compromise for mass production. The collaboration soured. The delays and disputes hurt progress more than any mechanical failure. Then, in 1943, a lifeline appeared. Stanley Hooker, a brilliant engineer from Rolls-Royce, himself an innovator in supercharger design, saw what was happening and intervened. Through quiet persuasion and the weight of his company's reputation, he arranged for Rolls-Royce to take over Rover's jet engine project. It was a turning point, though no one knew it yet. For Whittle, it must have felt like handing over his child, part relief, part loss. His vision was now out of his hands, growing into something larger, industrial, national. But that was the price of success. The jet age was no longer a dream in a cluttered workshop. It was becoming reality, forged in fire and war. And somewhere, in the fading hum of the test stand that evening, as the last engine cooled and the metal ticked softly in the silence, one could almost hear it, the quiet exhale of a machine that had learned to breathe. Rolls-Royce had long been a name synonymous with quiet precision and mechanical perfection. Its engineers understood the rhythm of metal, how it breathed, flexed, and carried power through its veins. When the call came to adapt that mastery to Frank Whittle's bold new engine design, the company moved with remarkable speed. The transition was swift and seamless, and before long, the Rolls-Royce Welland, derived from Whittle's W2B, began rolling off the production lines. The hum of industry filled the air again, this time with a different promise. In parallel, work on the Gloucester Meteor, Britain's first operational jet fighter, advanced steadily. On March 5, 1943, the first prototype took to the skies, its twin experimental engines singing a strange, unfamiliar tune, the sound of the future. The early flights were far from perfect. Test pilots wrestled with instability and control problems, the kind that can turn a moment's hesitation into disaster. Each return to the airfield brought a list of adjustments, a battle of patience between human intuition and untested technology. Yet, day by day, the Meteor evolved. By July 1944, nearly 3 years after Whittle's E-2839, first defied gravity, the Royal Air Force's 616 Squadron received its first operational Meteors. These sleek, engine-bright aircraft would soon face their baptism of fire, defending British skies against the terrifying V-1 flying bombs that rained destruction over London. For the first time, British jet fighters entered combat, a turning point in history, though one tinged with humility. The Germans had reached the milestone earlier. The Luftwaffe's Me-262 had taken flight as early as July 1942 and entered service by April 1944, just 3 months before the Meteor. Capable of speeds exceeding 850 kilometers per hour, it outpaced every Allied piston-engine fighter with ease. For the Allies, its appearance was like seeing the future arrive on the wrong side of the front line. Yet fortune, or perhaps human stubbornness, intervened. Adolf Hitler had insisted that the Me-262 be adapted as a fast bomber instead of a dedicated fighter. That single strategic blunder slowed its deployment and blunted its impact. Had squadrons of Me-262s been unleashed purely as interceptors from 1943 onward, the skies over Europe might have told a darker story. The Meteor, slightly less advanced but more reliable, became Britain's quiet answer. Its smooth acceleration, steady controls, and the absence of a propeller gave pilots new confidence. Forward visibility improved dramatically, no spinning blades to blur the horizon. The engines offered not only speed, but stability. The flight was smoother, less exhausting. Pilots emerged from missions less shaken, more aware of the possibilities that lay ahead. By the war's end in May 1945 in Europe, and that August in the Pacific, jets had barely made their mark on the battlefield, arriving too late to decide the conflict. But those who understood technology could see the truth. The world had changed. The age of the propeller was fading into history's mist, replaced by the whine and whisper of jet propulsion. Frank Whittle himself rose through the ranks, promoted to Air Commodore in 1943, and showered with honors in the post-war years. In 1948, he became Sir Frank Whittle, a Knight Commander of the Order of the British Empire. Yet behind the medals and ceremonies was a quiet sorrow. For the invention that had redefined flight, he received only $10,000, a sum that felt almost insulting compared to the immense commercial and strategic value of his creation. Years of bureaucratic resistance and personal sacrifice had left him drained. He left the RAF that same year, body and spirit both worn thin by relentless strain. What followed was a long, slow unraveling of exhaustion. Whittle suffered from nervous fatigue, not the kind a few days of rest could cure, but the kind that seeps into one's bones after years of pushing against disbelief. For a brief time, he worked as a consultant with BOACE, the British Overseas Airways Corporation, but soon withdrew from the noise of industry to live a quieter life. Meanwhile, his creation, the jet engine, began to transform the skies. In 1952, the de Havilland Comet became the first commercial jetliner to enter service. It could soar higher than mountain peaks, faster than any prop-driven craft before it, gliding above weather and turbulence with an almost dreamlike smoothness. The age of mass air travel had arrived, shrinking continents and making intercontinental journeys an attainable reality. The United States, which had initially lagged behind in jet development during the war, quickly caught up. American companies licensed British technology, absorbing its core principles and building upon them. Within just a few years, firms like General Electric and Pratt & Whitney were producing engines that rivaled and eventually surpassed the British designs. The evolution was staggering. By 1950, barely 9 years after that first experimental flight of the E-2839, jet engines had grown tenfold in power. By 1960, engineers were perfecting high bypass turbofans that offered efficiency unthinkable in the piston era. And by 1970, supersonic transports like the Concorde cut through the stratosphere at twice the speed of sound, a silver dart across blue infinity. Progress had become a whirlwind, almost faster than memory could keep up. Today, every major aircraft, military or civilian, draws its heartbeat from the same principle Whittle first envisioned. What began as a crazy idea in 1928 had become the global standard, carrying billions across the world each year. The foundational concepts Whittle pioneered remain at the core of every jet turbine that lifts from a runway. Frank Whittle lived long enough to watch his once ridiculed dream reshape civilization. In 1976, he moved to the United States and accepted a teaching position at the U.S. Naval Academy in Maryland. Even in his later years, he kept working, refining, questioning, exploring, that same restless curiosity still alive behind tired eyes. He passed away on August 8, 1996, at the age of 89 in Columbia, Maryland. His story endures as a testament not only to genius, but to endurance, the quiet, stubborn kind that bends without breaking. He had known failure intimately, dismissed by officials, ignored by investors, and forced to watch others advance ideas that had once been his lonely crusade. Yet he never surrendered. His life stands as proof that revolutionary ideas rarely emerge welcomed. They challenge, they disrupt, and in doing so, they attract resistance. But time, guided by persistence, has a way of vindicating the visionaries. Today, when you sit in an airliner and feel that deep, rising thrust pressing you into your seat as the engines roar to life, remember that it all began with a young cadet who refused to give up on an impossible dream. Remember the countless nights of frustration, the burnt fingertips, the notes filled with half solutions and hope. The jet engine didn't just alter technology, it altered the rhythm of human movement, the way we see distance and possibility. Frank Whittle didn't simply invent a machine, he redefined the sky itself. And somewhere, even now, as a modern jet streaks silently through the thin, cold air above the clouds, its echo carries the faint whisper of that first impossible idea, the one that dared to fly before the world was ready to believe.